welcome on board. This is Design DU Engineering Process, a channel where we give a walkthrough on process engineering operations and design. Let's dive in. For today's content, we're going to be biting on a little bit more than we can chew, but hopefully we do have enough water on the table to help us swallow. We're going to be looking at the 9th equipment in our model palette, which is the separator, traditionally known as the 2-phase separator, the 10th equipment, which is the 3-phase separator, 11th, which is the tank, 12th, the compressor, and the 13th, which is the expander. It seems like a lot, but we're going to make do with time to see how far we can go in a short period of time. So, for the new viewers, as always, we will advise you to go through our previous content to avoid getting lost during today's content. The link will be dropped in the description. Let's get started. What is a separator? A separator is an equipment used in process industries such as oil and gas, petrochemicals, or chemical plants to split or separate a mixture of substances into two or more different phases or components. Separators exploit the physical difference such as density, phase, or solubility of a certain mixture to achieve separation. What this basically means, this exploiting of physical differences, it means for you to actually separate, you do need to consider the type of mixture you're having. You need to consider factor. You need to do a background check, a little bit of a research to actually know what separation technique is more suitable and more efficient for separating a particular mixture. So let's say, for example, I have crude oil, and we do want to separate the different components of the crude oil. We do know that it's fractional distillation. Distillation basically, but to be more specific, it's fractional distillation. So you do know that that's the separation technique which is more efficient for separation of crude oil, fractional distillation. For example, if you do want to carry out air separation, separating nitrogen from oxygen in your air mixture, you do carry out a cryogenic distillation. So it's more of a background check thing. It's not a blind thing. It's not all about connecting the equipment in the Aspen Hysys, even though it's modeling and simulation, but you do need to work with the background check, the research, to actually know what separation technique is more suitable. So at this point, it's going to be different. It's going to take a whole ton. The whole beginner's journey for the Aspen Hysys is going to take a very huge ton. It's not like the previous contents where we do just connect our equipment and just work with any variable. From this point on, we do need to work with certain real-life information to make sure that our designs are more suitable and more efficient. So with that, we do know that separators exploit the physical differences between density, phase, or solubility of a certain mixture for separation. For the density, let's say, for example, for density, if you do want to separate water and oil, you do know that water is more dense than oil, so you expect your oil to be at the top layer of the water. So the oil is going to be the first layer and the water is going to be beneath the oil. So with that, you do know that their densities are different, and you do a little bit of a research to know what separation technique is more favorable for you to actually separate them. So a separator, this is what a separator looks like. The schematics for a separator, 2-phase separator in our case, and it's a vertical 2-phase separator. We have two types of 2-phase separator, the horizontal and the vertical. Let's look at the difference. As the name implies, the vertical, of course, is in the vertical form. This type of separator is suitable for separating a mixture which has more gas. The mixture is made up of more gas than liquids. Let's say, for example, you have 60% gas and 40% liquid. You make use of a vertical separator. You have the mixture inlet, which goes into the separator, and the gas outlet at the top, because gases are light, so they tend to go up, while your liquids go down in a vessel. So the liquids are at the bottom, liquid outlet, and the gas outlet at the top. That's for a vertical separator. For the horizontal separator, 2-phase horizontal separator, it's horizontal, as you can see. It goes into the mixture goes into the separator, and you have a gas outlet at the top and liquid outlet at the bottom, just like the vertical, only that this is horizontal, and you use the horizontal 2-phase separator to separate a mixture having more liquids than gases. So let's say, for example, you have 60% liquids, 40% gas in your mixture. You make use of the horizontal separator, horizontal 2-phase separator to separate your mixture. In Aspen Hysys, take note, it doesn't really affect your your final product, or what I call it, the process end product of the process. Whether you use a vertical or horizontal separator, you're more likely to actually have the same value when using the vertical separator and the horizontal separator for a scenario where you have more liquids or more gases in your mixture. But in the real life scenario, we do apply this particular design this particular design format, the horizontal and the vertical separator. So remember, the vertical is for a mixture having more gas. The horizontal is for a mixture having more liquids. That's about it for the two-phase separator. Moving to the 10th equipment, which is the three-phase separator. Similar to the two-phase separator, the only difference is that it's a type of separator that separates oil, gas, and water mixture. So basically, it separates a mixture, but then this time around, it's having 3 outlets and not 2 outlets. A gas outlet, a light liquid outlet, and a heavy liquid outlet. The oil is more dense. Oil is lighter than water. Water is more dense, so you expect that the water is going to be the heavy liquid, the oil is going to be the light liquid, and the gas goes up from the top. So that's the 3 outlets, and as always, you have your single inlet of your mixture, the mixture inlet basically. So the 3-phase separator. This is what the 3-phase separator looks like. The inlet, mixture inlet, the heavy liquid outlet, the light liquid outlet, gas outlet. So you expect your oil to be inside your light liquid outlet because it's lighter. The heavy liquid, which is the water, goes through the heavy liquid outlet, and the gas through the top, the gas outlet. For a more detailed schematics, this is what it looks like, the 3-phase separator in the process of separating a mixture of gas, oil, and water. You expect that the water follows the heavy outlets, the heavy liquids outlets, the oil follows the light liquid outlet, and the gas follows where it's supposed to, the gas outlet. This yellow thing we have on our screen, we could just go back. This yellow little thing is aware. It's basically the boundary separating the outlets of the light liquid outlets from the heavy liquid outlets. Its function is to prevent the water from actually following the outlet of the oil. Basically, the light preventing the heavy liquids from following the light liquids to move out of the separator. With that, you wouldn't have an efficient separation of your mixture. So it basically prevents the water from going out with the oil. So basically, this is what a 3-phase separator looks like. It's an equipment used to separate a mixture of gas, oil, and water. So in a scenario where you do have crude oil having a mixture of gas, liquids, and water, this is a very good equipment used to actually separate the mixtures. Storage tanks. A large container equipment used to hold liquid or gas for an extended period of time in a process plant. Types of tanks include above ground storage tank, the abbreviation AST. As the name implies, it's above ground on ground level. Although it basically takes up a lot of space for it to actually be situated on ground, but it has this easy feature of easy maintenance, so it's very suitable. For the underground storage tank, as the name implies with the abbreviation UST, it's underground. It takes lesser space on ground because it's underground, so you do have more space on ground to do other activities or drop other equipment. But then it has a little bit more complex maintenance issues, unlike the above ground. Then we have the fixed roof tank. Basically, the roof is permanently fixed. The top of the tank, it's permanently fixed. It doesn't move, and you only use this type of tank to store stable liquids, meaning liquids that do not easily vaporize. In an event of vaporization inside a fixed roof tank, pressure is exerted on. When vaporization takes place, gases are formed, and as a result, pressure increases inside the tank. inside the fixed tank, and with that, you do have pressure being exerted on the body, the whole structure, the body of the tank, which could actually lead to accidents or deformation of the tank, basically damage. Floating roof tank. This is the tank used to store liquids which are not very much stable, liquids which easily vaporize, because the roof isn't permanently fixed. It's basically always laying on top of the uppermost layer of the liquid. It's laying, so in an event where the liquid goes down, the roof goes down with it, and if the liquid goes up or there's a pressure buildup where vaporization takes place, gases are formed, pressure builds up, it goes up for it to actually accommodate for the pressure that has built up. So this is a type of tank, floating roof tank, as the name implies. This is a type of tank used to store liquids that are not very much stable. And in an event where you're trying to store a substance, liquid or gas, which has a tendency to exert pressure, excessive pressure inside the tank, you use a pressurized tank, this is a type of tank that is specially designed to withstand high pressure. And that's it for the types of tanks. So a liquid storage tank is mostly cylindrical in nature. And as for the top, it's not always flat. Sometimes it's conical and some other shapes. It's designed to preference and some other design features that want to be attained for a process. So having a cylindrical shape, you store liquids inside the tank. You store liquids inside a cylindrical tank. In an event when you do store gas inside a cylindrical tank, chances are that force is going to be exerted in this uppermost layer where you do have edges. Forces might be exerted on them due to the excessive pressure buildup of the gas. And with that, it could lead to accidents such as explosion, deformation, and some other things. On the right hand side, as you can see, this is what the tank might look like if it's deformed. Although this looks very, very nice, but just to get an idea where the edges, excessive force being exerted on the edges of the cylindrical tank, it deforms it and it just changes the whole shape of the tank, and in some event it can be catastrophic, leading to explosions and other accidents. For the gas storage tank, it's stored. This is not a circle, don't worry. It's a sphere, but we cannot bring out the whole 3D dimension, so we represent it in a circle. The gas is stored inside a spherical tank. The reason for this is that, remember, the gases do exert pressure due to the gas, the nature of the gas. So you do need a structure which has no edges, and the best shape for the storage of gas would be a sphere, because a sphere has no edges. If you actually visualize it, it has no edge. It's just basically the circumference keeps going round and round and round and round, no edges. So it's the perfect shape to actually build a gas storage tank, and that's what is used to store gases, a spherical tank. And for the liquid, it's a cylindrical tank. So our 12th equipment, if I'm right, the compressor. A mechanical device used to increase the pressure of gas by reducing its volume. As a result, temperature increases. So remember our usual temperature is a function of pressure, torque, direct proportionality, Gay-Lussac's law, ideal gas law. Increase in pressure leads to an increase in temperature. So the compressor is basically like the pump, only that it increases the pressure of gas, in this case, not liquids. This is possible due to the compressible nature of gas, unlike liquids. For the liquids, remember, they're incompressible, and as a result, the pump utilizes the incompressibility factor to move the fluid from one point to another, as energy is being exerted to the fluid. It moves it from one point to another. But for the gas, it's compressible, and with that, it reduces the volume of the gas, the gas occupies. After that reduction in volume, pressure is being significantly increased. With this, the gas gains pressure. So that's basically the function of a compressor. You could say it's the opposite of a pump, in the sense that it increases the pressure of a gas, while the pump increases the pressure of a liquid. And just like the pump solely pumps 100% liquids. The compressor the compressor also increases the pressure of only gases. No mixture, no liquid, 100% gas. Types of compressors. Compressors include centrifugal compressors, axial compressors, reciprocating compressors, screw compressors, turbo compressors. Then the 13th equipment is an expander. This is simply the opposite of a compressor. If a compressor increases pressure, then the expander decreases pressure. A mechanical device used to reduce the pressure of gas by increasing the volume of the gas. Remember, the compressor reduces the volume of the gas, thereby increasing the pressure due to the force being exerted on the gas for it to reduce its volume that it occupies. But whereas in the expander, the gas is being expanded. With that, the pressure is dropped. The pressure being exerted on the compressed gas right now is expanding. With that, the pressure is dropping, and as a result, temperature drops due to our Gay-Lussac direct proportionality temperature between temperature and pressure, as we have always been seeing. Types of expanders include centrifugal expander, axial expander, turbo expander, and with that, we are done with the whole theory, blah, 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 blah. Let's head to the modeling environment. We're back to the modeling environment. So, as always, set a model, we drop streams. We're going to create a stream, and for today, our components are H2O and hexane and hexane. So let's head to the component list. I've already selected my components and my fluid package. My fluid package is Penn Robinson, as always. For the new viewers that do not know how we got here, the link is going to be in the description. As always, that was our very first content. Make sure to watch to be on track with us. So 50% H2O, that should be our composition, and 50% hexane. With that, we have a mixture in terms of composition. We do have a mixture. All right, so we come down here. Let's give it a temperature of 30 Celsius. 1 atm for our pressure. 1 atm, which is equal to 1.013 bar. And a molar flow of 500 kilogram per hour. With that, we've successfully created our stream. Let's name this mixture for easy reference. All right, so I need you to take note of these 4 parameters. First 4 parameters, they're very important. The vapor fraction, which is 0, signifying 100% liquid. Temperature 30 Celsius. Pressure 1 bar, 1 atm. Molar flow 500 kilogram mole per hour. Take note of these 4 parameters. With this, we have successfully created a stream, and we will drop a separator. That's the 9th equipment, traditional 2-phase separator. Remember, for the equipment, you connect your inlet and label your outlets. And the separator is no different from the other equipment you have been handling. So this is the vapor outlets at the top, which signifies the gas outlet, so the gas. Then we call this the liquid outlets, where the liquid would pass. And with that, after imputing our inlet, labeling our outlets, the separator automatically solves. So on the left-hand side, at the bottom, you can see that we do have a column for energy, the energy stream. We do not need to label the energy label because in brackets written here, it's optional. So you mustn't really add an energy label, an energy stream to the separator. All you have to do is impute your inlet, label your outlet, and it automatically solves. So I need you to look at this diagram, the separator diagram up here. It's a vertical separator, like the one we had back in our presentation. This is a vertical separator, which means it is more suitable for separating a mixture that has more gas. But remember, in Aspen Hysys, it doesn't really matter which you use. Your end products tend to be the same most cases. So, but to always make things look more realistic and more more proper, more engineering wise, and more professional, we do tend to stick with the real life operations in most cases. So up here, as you can see where my cursor is, we have a funny rectangular shape with some X's inside. It's nothing more than a thermistor. It's more like a top layer just before the gas outlets, which traps any liquid that goes up together with the gas. In some cases, you do have the gas, a wet gas, the gas being moistured. And remember, in the gas outlet, we do not want any phase apart from gas, 100% gas. So the function of this it's more like a padding. The function of this padding is to actually trap any liquid attached to the gas, which tries to escape through the gas outlet. If there is any liquid, it just traps it. It's more like a pad, with a fabric pad, I would say, maybe, or something that could actually trap moisture, that could actually trap water. So that's what it does. When the gas moves above it, the gas is able to pass through the demister, and then the water molecules are being trapped in the padding. And after a period of time, when it gets drenched with a lot of moisture, it starts to drip. The water being trapped in the padding starts to drip down back to the bottom, where it goes out through the liquid outlets. So that's what it basically is. It's more like an extra layer to separate the little liquids that are attached to the gases, which try to actually escape through the gas outlet. But it doesn't really matter in Aspen Hysys, because Aspen Hysys does the separation efficiently, but it's just an extra tip for knowledge. So with that, we've successfully operated our separator. Now time to actually check to see how efficient was our separation. To do that, we will be clicking on the gas outlet at the top. So take note of the first 4 parameters. Let's compare with what we had in our, I think we could just match this a little bit. Yes, much better. Then we can open up another one for our inlet. All right, so let's compare. First of all, our phase fraction for the mixture, that's the inlet, it's 0, and for the gas outlet is 1, and it makes sense because the gas is supposed to be 100% gas in the gas outlet, so that's what it is. The temperature is the same, 30-30, the pressure is the same, 1 bar, 1 bar. But then the flow rates, actually the 3 flow rates, molar flow rates, mass flow rates, steady, ideal, liquid, volume flow rates, are all 0 for our gas outlet case. So when something is 0, that means it's empty basically. And what this tells us is that the gas stream is empty. When the flow rate is empty in a body, it means there is basically nothing flowing through it. So the gas stream has no gas flowing through it. It's basically empty. And there's a reason for this, but let's look at our liquid outlet stream first of all. So I just shift this a bit. Good. And for the liquid, we can compare. Everything is the same. Everything is the same with the inlet, the mixture inlet. The liquid outlet is the same, every single thing. And then we just take a look at the flow rates. As you can see, the flow rate at the liquid outlet is the same with the flow rate that went inside. It's more like the continuity equation of what goes in was amount to what comes are provided there are no accumulations or losses in the system. Remember, Aspen Hysys works perfectly with the assumption that there are no losses or accumulation within a system. So what goes in was equal to what comes out. And remember, for the gas outlet, we're having 0, which means nothing was coming out. So the whole 500 going inside the separator came out through the bottom. That's why we have 500 kilogram mole per hour as our flow rate. The same thing that came in went out through the liquid completely. And the reason for this is that this is our mixture. The vapor fraction is completely liquid. Remember, the separator banks on factors such as density, phases, to actually separate the mixture into distinct components. In our case, our components are H2 and hexane. But then the phase, they are all in the same phase. So how do you separate them when they're all in the same phase? The separator wouldn't be able to separate them because it can't bank on that factor of phase. So the separation wouldn't really work. It's just basically as long as it's in the same phase, it's just going to basically follow one path, all of them, and they all go out without any separation. So for you to actually be able to separate a mixture, you need to consider the separation technique for that particular mixture to know which is favorable. And this is where the background check comes in, the research, to actually know what separation technique is suitable and more efficient for your process. So we have different types of separation techniques. You could say distillation, evaporation, condensation, gravity separation, decantation. They all do have their particular areas of application. But for this scenario where we're having liquid, the same phase, and our components are H2O and hexane, we can bank on the separation technique, such as the separation technique that deals with their boiling points. Because if you do a check, you would see that the boiling point of hexane is around 68.9 Celsius, and at 1 atm, atmospheric pressure. That is what we are working with. And for H2O, the boiling point is 100 Celsius at 1 atm also. So you can see that their boiling points are far apart, and you can use the separation technique that has to work with their boiling point to separate them. And that particular separation technique is called evaporation, basically using their boiling point to separate them. In an event where we do have the particular, where we do make use of the evaporation, the liquid with the lowest boiling point, with the lowest boiling point, would evaporate first. And in our case, that's hexane, because hexane is around 68, 69, and water is 100 Celsius. So we expect that our hexane would evaporate immediately, reaches that temperature of 68, 69 Celsius. It would evaporate to gas while leaving us with the liquid, H2 as our liquid. So with that, you could separate the mixture of hexane and water. So in order for us to do that, to do evaporation, we would need to simulate an evaporation process, and evaporation basically entails the act of heating a liquid to change its phase from liquid to gas. And for us to do that, we will be using the equipment that we have worked with before. That's the heater. I believe that should have been our second content, and the link will also be down in the description. So make sure to watch that to be on the same page with us also. So we are currently on pause, and all we did was just basically disconnect. We could just do that again. We could just kindly do that again. Yes, so this is how it looks. We go on hold, and then we right click, and we have this function called break connection. And with that, we have disconnected the stream from the separator. Then the other way to also do that is, let's just add the stream back. So we currently have our mixture stream connected, and you could just click on this and hit the delete button on our keyboard, and with that, it separates it. So those are two ways to actually break the connection. So in order for us to carry out evaporation, in the process of carrying out evaporation, we do expect our temperature to change and our vapor fraction. So we will be using a heater. That's the third equipment. We will connect our mixture to the heater to hit that temperature where evaporation takes place. That's the boiling point of hexane. And then at that stage, we have a mixture. Inside our mixture stream, we have a mixture of gas and liquid. The vapor fraction basically changes, and then we send it to a separator to do the separation of the two components. That's the hexane and water. So inside our cooler, we add the inlet, the mixture inlet. Then remember, the heaters do require energy streams. We call it heater. Then the outlet, we can call it heated mixture. And then remember, we need to specify our change in pressure. But before we do that, remember we're on pause. So let's put this back on play, active. And then change in pressure, we could just, we could just probably have a 1.5 bar. Or let's still work with our Let's still work with our 1 atm. And then let's specify a temperature of about 69 Celsius. That's the boiling point of hexane. At this point, we expect that the hexane would evaporate and start turning to gas to leave the water as our liquid. All right. You could see with that we have a vapor fraction of 0.7005. So with this, we currently have a mixture. We basically have 70% gas and 30% liquid. And with that, we have more gases, and our horizontal separator will be the right separator to use for the process. So we could just connect this heated mixture to our separator to carry out separation. Like this, we have successfully operated the separator, and we can now check our gas outlet to see what we do have. And we currently have a flow rate. Unlike our scenario earlier where we had zeros, this time around we do have a gas because we have a mixture, 70% gas and 30% liquid entering the separator. So let's check our composition. And as you can see, we do have 70% hexane and 29% H2O. What this basically means is that we have more of gas, the hexane is more, and obviously because the hexane has the lower boiling point of 69 Celsius, so it evaporated first, but then unfortunately a little bit of the heat water followed the evaporation process and went up as gas too. So we'd have to work on this. We'll be back to it shortly to see how we can make the separation process more efficient to have more hexane at the top and more liquids at the bottom. And then down here too, we do have a flow rate of 147.3. We do have a content of water down here, basically a liquid content in our liquid outlet. And as you can see, we have completely H2O. And the reason for this is, remember, that H2O has a higher boiling point than hexane. So we're not able to reach that particular boiling point where water completely evaporates. So we completely have water at the bottom and we have no hexane because we have already hit that boiling point of hexane. But unfortunately, a little bit of our water went up with the hexane. And fortunately, we're able to boil off all the hexane from the uppermost layer of the liquid. We're able to boil off all the hexane, basically evaporating, and it went up through the gas. But unfortunately, some of the water followed it, so we will have to probably drop the temperature a little bit so that a little condensation takes place and some of the water drops down so that we do not evaporate a huge amount of liquid to lead to a scenario where the H2 follows the hexane. So let's just basically say this is 68 and not 69. Okay, with that our vapor fraction is 0.69. So let's check and see. All right, so as you can see, what we have right now is 27%. So let's just work with this too. Let's keep tempering with the temperature a bit to see how we can achieve an optimal separation. Let's say this is 65. All right. That it keeps going down. Let's say this is 60. All right. As you can see, more water is going down. More water is going down. So let's say 59. We currently have 79% of hexane and 20% of water. So let's make it 45. Let's see. Let's say this is 45. We heat it to a temperature 45. And as you can see, we have 83% hexane, 16.9% water. Let's make it 40. Let's make it 30. Okay. Let's make it 35. All right. So Or let's try the lowest temperature. Let's say 31. Okay. So, but then our vapor fraction dropped to 0, which isn't a mixture. So with that, the separation cannot efficiently take place. So let's put that 40 one more time. 50. We have to make sure that our vapor fraction is anything other than 0. 60. 68. Let's try 67. 65. 61. Vapor fraction is down to 0 again. 62. Good. So it's telling us that at a temperature of 62, our vapor fraction turns to 0.6. Basically, that's where the evaporation starts. Not the temperature of 68, but at the temperature of 62, that's where the evaporation occurs, where the liquid starts to turn to gases. And at that temperature, we would be having a composition in our gas outlet. Remember, we're in the gas outlet. We'll be having a composition of 78.8% hexane and 21.20% H2. So basically, this is the best we can achieve with this separator. With one separator in this process, this particular evaporation process, we can achieve about 68.8% separation of the hexane from the water. So the hexane purity, basically, we would say the hexane purity is 78.8%, and we do have 21% of water at this particular conditions that we do have up here. So let's check the liquid and see if we still have 100% H2O down at the bottom. Yes, we could. The H2 is still 100% H2O, no hexane, because all the hexane evaporated, unfortunately, with some water. So with this, we can say that we can achieve separation, a purity of 78% for the hexane, about we could 78.8% with the evaporation separation technique. But if we were to use other maybe secondary separation techniques, we could say that we would drop another separator to keep separating and separating until we're able to actually separate the whole water from the hexane, basically the mixture, to completely separate them 100%. Using the evaporation technique, we would be able to keep doing a series of cooling, because right now what we have is gas. We do have gas. The steam, basically we would say steam, gaseous water inside our gaseous hexane. So if we do a little bit of cooling and separation again, when we cool, the vapor fraction drops from 1 to 0 point something, and then we drop a separator, and we can, with that at the bottom of the second separator, we would be having water at the bottom. So we could keep doing a series of this cooling and separating until we're able to actually separate them completely 100%. But that takes time and is a little bit too stressful. And so there's another separation process that could just combine the whole series of cooling and separating to just one technique, which is basically called fractional distillation. We could just use a distillation column to just do the whole separation, and you would separate them maybe 90-something% purity. If we're fortunate enough, we might be able to get 100% purity between the water and the hexane to completely separate them from the mixture. But that's we're going to look at the distillation column hopefully in our next content. But with this, we have carried out the separator using a vertical separator to separate the mixture. So let's turn things around this time around. Let's say we're using, let's just delete this. Let's say we are using a horizontal, or rather, we could just, to change it, because in our model palette, the separator we do have here is a vertical two-phase separator, but to change it to a horizontal, all we have to do is just right-click on this, go down to change icon, and then you can see the series of separators there, and you just move this cursor to go back and front, and this is the vertical separator, the horizontal two-phase separator rather. Click on this, okay, and it turns it to a two-phase horizontal separator. And if we check, we would see that our composition is still the same. Nothing changes. Nothing changes in Aspen Hysys. When you use the vertical horizontal separator, it's all the same thing. When in real life applications, we use the vertical for a mixture that has more gases and the horizontal for a mixture that has more liquids. So as you can see, we still have the same 78.8% and 21.1% of our hexane and H2O respectively in the horizontal separator. The same thing we had when we were using the vertical separator. So it doesn't make any much of a difference. This is basically it. So with this, we have covered the two-phase separator, both the vertical and horizontal. So let's try and cover up the three-phase separator. So for three-phase separator, we're going to be using a component of H2O. Remember, three phases, so it's going to separate water, heavy liquids, light liquids, and gas. For our composition, our components are going to be H2O, 40% H2O, 30% hexane, and this time around we added methane to be the third outlet. That's the gas, 0.3%, 30% rather, 30% methane, 30% hexane, and 40% H2O. So in this case, the methane is the lightest, and in a natural form, methane exists as a gas. So methane is going to be the gas, what goes out through the gas outlets, and then hexane. Hexane is lighter than water. Basically, water is denser than hexane. So hexane is going to be the light liquid, and then H2O is going to be the heavy liquid. So basically, we're going to be having our gas outlets, having methane pass through our gas outlet, having hexane pass through our light liquid outlet, and then having H2O pass through our heavy liquids outlet. And for this, we're going to be using the same conditions: 30 Celsius, 1 bar, which is basically 1.013, 1 ATM radar, which is basically 1.013 bar, and then 500 kilogram mole per hour as our molar flow rate. And as you can see, when having all these parameters, our phase fraction is basically a mixture, naturally a mixture, 0.4233. That's our vapor fraction, our phase fraction, telling us that we do have 42.33% liquids. Yes, 42.33% liquids. Is it liquids? Yeah, liquids in our mixture. So the mixture basically entails of more liquids than gas. But it doesn't really matter for three-phase separator, because three-phase separator is always horizontal. It's in the horizontal form. So with this, we already have a mixture because of the methane that is inside the mixture currently. Methane is a gas in its natural form. So it's already a mixture. We do not need to do any form of cooling to achieve any separation. It's already a mixture. So we just drop our three-phase separator, which is the 10th equipment. We drop it down here. And then double clicking, this is how the interface looks like for a three-phase separator. Just like the two-phase separator, the energy label is optional. So all we have to do is impute the inlets and label the outlets. So our inlet is the mixture, the outlet is the gas, the vapor outlet is the gas, the light liquid should be, we could just call it oil, and then the heavy outlet should be water. This okay, and it just automatically solves when we label them. And then as you can see, we do have 3 outlets and 1 inlet. So let's check our gas and see if we have anything in our gas outlet. And yes, we do. We have a flow rate of 211.7 out of 500 kilogram per hour. We have 211.7 down here. So let's see what we do have. Okay, so we predominantly have methane because methane is more of the gas, 7.070 as our methane. That's what we do have as our methane. And we 70.7% methane, 25.17% hexane, and then we have we do have 4% H2O, 4%. Is that 4%? 1, 2. Yes, that's 4% H2O. So you can see predominantly have methane because that's more of the gas, and a little bit of the hexane is in the gas form, and a very little bit of the H2 is in the gas phase. So for the oil, which is our light liquid, we also have a flow rate there. It's 7.15%. That's what we do have for our flow rate. And then, as you can see, the H2 is very, very small. We have a 0.6% H2O, or we have the less than 1% water, because more of the water is in the gas, and a little bit of the water is in the gas outlet, and more of the water should be in the heavy liquids outlet. For the methane, we have a little bit of methane also, 0.3%, 0.3% methane, and 0.06% H2O, and we predominantly have hexane, 99.57% hexane in our light liquid outlets. That's where the hexane is supposed to go out, obviously. And then for the water, we do have a flow rate of 191.2%. Oh, sorry, 191.2 kilogram mole per hour as our flow rate. And then we completely have water down here, 100% water. No other component followed the water down here. But then the water followed a little bit of the gas and a very, very little bit of the hexane. So with that, we have successfully operated the three-phase separator, but we haven't efficiently separated them. So you need to take note that, like we said, the separator also obeys this continuity equation thing of where what goes in must equal to what goes out. And if you add up the molar flow rate of the three outlets, is going to be equal to the flow rate of the inlets, that 500 kilogram mole per hour. If you add the flow rate of the gas outlet, the molar flow rate of the gas outlet, the molar flow rate of the oil outlet, and the molar flow rate of the water outlets, they are all going to equate back to 500 kilogram mole per hour that went inside the separator. So there are no accumulations or losses. With this, we have successfully operated the three-phase separator. But let's see if we could actually do a little bit of an optimization to achieve a more efficient separation. In this case, we have a vapor fraction of 0.4233. With that vapor fraction, we do have our composition to be 70% methane, 25% hexane, and 0.413 4.13% H2O. So let's see if we can do anything to actually make this H2O drop down to where it's supposed to be, the water outlets. That's basically the heavy liquid outlets. And to do that, we expect a condensation. What it's basically telling us is that the mixture is actually more of a vapor. It's too hot, so as a result, the vapor fraction is very high, which results to the water evaporating together with the methane to actually follow up and go out in the gas outlets. I'm sorry if I sound a little bit off track, but it's going to make sense in a jiffy. So we're going to disconnect this and do a little bit of condensation so that the water present inside the gas outlets would be where it's supposed to be in the water. Okay, we lost the data because we disconnected the inlet stream. So to do a little bit of the condensation, we're going to be using a cooler because it drops the temperature, and as a result, the gases would turn to liquid. So we're going to connect our mixture, the mixture, that's the inlet stream, and then call this E cooler, okay, and call this the cool mixture, okay, and then specify a change in pressure. But let's put this back on active. Let's leave that same temperature of 1 atm, and then let's give this a temperature of 20 Celsius. It cooled to 20 Celsius, and with that, our vapor fraction drops it 36 points. It drops to 0.3676. That's our vapor fraction. So With this, we will now connect the cooled mixture to the three-phase separator. And after doing that, let's see if our water dropped down to where it's supposed to be. Yes, as you can see, our methane spiked up from 70.7% to 81.3% because we had condensation. So the water that was up here, the water that was up here dropped, and even the hexane, it was around 22.2%. 22.2%. So it basically dropped to 16%. So let's do a little bit of more cooling and see. Let's check the oil stream and see what it looks like. Let's check and see. Good. We still have more of hexane, 99.5%. Then we have 0.4%, 0.45%, and 0.04% H2O, 0.45% methane. So this is perfect. And for the water, we still have 100% methane. So let's see if we could, for the gas, we still do have, okay, I think we're inside the gas. Yes, we are inside the gas. We still have about 2% of H2O. So let's see if we could just do, let's see if we could do a little optimization to drop it from 2% H2O down to like 1%. To do that, we will need to attain more condensation and we would simply cool more. So let's say it's 15 Celsius. Aha, with that we do have 1.6% water inside. So let's drop it down to like 10. Okay, let's drop it to like 5. Aha. Let's drop it to like 1. Good. We could go a negative. Let's try going a negative. -5. Aha. And that's not good for it. So let's say -2. Good. That works. Let's try -3. -4. Let's try -5 one more time. It also works. So Aspen Hysys sometimes gives this dumb error of a particular figure not working, and when you impute it gradually, instead of going from like 1 Celsius to -5 Celsius, it might give you an error. You could just do it bit by bit until you get there. Sometimes it works better like that. With that, we have a -5, and what we do have for our water inside our gas stream is 0.4%. 0.4%, 0.4% methane, 0.4% H2 inside our gas outlet. So it's less than 1. And for the hexane, we have a 4.78% inside our gas outlet, and predominantly have 94.8% methane inside our gas outlet. And for the oil, let's take a look and see if we're still okay. Good. We have 99.3% hexane. And then for water, we have a purity of 100%, completely water inside our heavy liquids outlets. For the light liquids, we have a purity of 99.36% hexane. We have a little bit of octane, very, very, very minute octane, 0.6, basically 0.63% methane, and then 0.01% water. Very as good as insignificant, basically. So with this, we carried out a 3-phase separation process using a 3-phase separator. So with this, we have covered the separators. So to avoid wasting time, storage tanks. That should be the 11th equipment, I believe. Yes, storage tanks. And we're going to drop 2. There's nothing special in the storage tank. It's just basically you dropping a tank, attaching the stream to the tank, and that's all. It doesn't require any much of a brain work stress. But then a little bit of a heads up. Sometimes tanks are very funny in Aspen Hysys. They do behave like separators. You could actually use a tank to separate a mixture. Let's do that before we connect the tanks. Let's drop a new stream. And we're going to do this, our usual lazy, convenient thing of referencing the stream, defining the stream, copying the attributes of a stream. We're going to use our initial stream of mixture. Okay. And with that, we have the same thing for this stream that we're having for this mixture. They are basically the same. I copied the new stream from the attribute of the mixture stream. So 0.4%, it's already a mixture. So I'm going to double click on my tank, and this is how my tank looks like. The energy stream is also optional. So all we have to do is just connect the new stream. That's one that we connected. Let's name this gas. That's the vapor outlet, the liquid outlet, because the tanks do have, yeah, we already named the stream gas. So we can just call this like gas 2. The liquid, we could just call the liquid 2. Okay, with that, we've successfully operated the tank also. Remember, this is a liquid tank. So in Aspen Hysys, it doesn't really matter what you store inside what. You could store a gas inside a liquid tank. It doesn't really matter. But for the real life scenario, we have to make do of that concept of cylindrical tanks only for liquids and spherical tanks only for gases. But in Aspen Hysys, it doesn't really matter. But just as always, to keep things more professional and proper, we will adhere with the real life engineering design concept. So as you can see up here, what we have is a gas completely, and then it carried out a separation for us. Basically carried out a separation for us, just like the separator would do. So the tanks are very funny. They do behave like separators. You could actually use a tank to do a separation, but that's not desired because that's not the function of a tank. So it's always better, like we said, to stick to the engineering concepts to make things look more professional and proper. So to use the tank, you could actually change the tank too. So this is for the liquid tank, the spherical tank like the cylindrical tank like we discussed. That's for the liquids. And for the gas, it's supposed to be spherical. And to do that, you right click and click on your change icon, and you can see this is the spherical tank that we use to store gases. So it goes up here, this comes down, this goes up here, and this should be up here. We should be down here because this is also liquid. And let's drop another one for the heavy liquids also. The tank cylindrical for the heavy liquids. So let's connect them like we did earlier. So we're connecting water to this, calling this 1. Should we? No. Yeah, we could call this 1. We could call this 11. We're good to go. Then we could also attach this. You could attach the oil here. Call this 2. Call this 22. Okay, successfully created. Then we should attach the gas. Call this 3 and call this 33. Okay. With that, we've successfully operated the tanks. Spherical tank for the gas. And remember, it's a gas going in here, so we expect that there should be nothing. This bottom stream is the liquid. It's not supposed to be there initially, but then Aspen Hysys expects you to label streams the vapor and liquid outlets always for the equipment successfully be operated. So you just have to name it, but there is basically nothing inside. As you can see, the flow rate is 0, basically nothing inside. Then as for the gas is up here. You can see there is a flow rate, and the flow rate up here is 157.3. So let's check what goes in to make sure that what goes in is equal to what comes out. This is what's going in the inlet of the tank, the inlet of the gas tank, and this is the outlet of the gas tank. So you can see the flow rate for the inlet is 157.3 and the outlet is also 157.3. Continuity equation being obeyed. For the oil, it should be the same thing. Oil, remember, this is the light liquid, and so there are no gases. The gas is empty, and this is completely liquid. So at the bottom, we have all the liquids passing through continuity equation. The same thing for the heavy liquid too. We have it down here. We have flow rates, and for the gas of the heavy liquid, we have nothing zero because it's liquid. With that, we have successfully operated our should that be the 10th equipment? 11th equipment, which is our storage tank. All right, so then we could just continue and drop the 12th equipment, which is our compressor. Remember, compressor, the function of compressor is to increase the pressure of a gas. So, and this is a gas. This is a gas up here, the gas outlet of the storage tank. This is a gas, so let's check the pressure. It's currently at 1 bar, 1.013 bar. So let's say we're compressing and we're raising the pressure from 1.013 bar to like 10 bar. The inlet, let's connect it. That's 3. That's the gas. We connect it. Then the outlet, we could just call this compressed 3, because that's the name of the inlet, compressed 3. But then we have a message down here in red saying requires an energy stream, so we call this E-comp for the compressor. And then unknown duty, meaning we do need to specify something. And for the compressor, since we are working with pressure, we do need to change the pressure. We could just directly impute the pressure. There are 2 ways to do this. Remember, just like the control valve and the pump, you could do it down here from the worksheets, specifying your final temperature. And let's say the final temperature should be somewhere around 5.013 bar, 0.13 bar. All right, with that, we have a change in pressure of 4 bar, positive 4 bar, because when you do 4 bar plus 1.013 bar, that's our initial temperature. It gives us a initial pressure. It gives us a final pressure of 5.013. So our change in pressure is basically positive 4 bar. It gained 4 bar. And then, as you can see, direct proportionality of temperature and pressure. Temperature is a function of pressure. Increase in pressure leads to increase in temperature. So we have our temperature spiking up from -5 to 125.4. That's crazy, really, really crazy. So, a heads up, in an operation where you do want to increase the temperature of a gas, you could make use of the increase in pressure for gases and just drop a compressor instead of using a heater, because a heater is more expensive due to its operation costs, unlike the compressor. So you could just use a compressor to save costs and just increase the pressure, and then the temperature just goes boom up. You could do that. So that's one way to actually increase your your pressure. And the other way, you could just, let's raise this like we did for the valve in our previous content. You just go to the design, hit parameters, and you could see a bunch of things up here. Doesn't really matter for now. We're just working with the centrifugal compressor, reciprocating, and we do have a screw, just like we discussed in our presentation, types of compressors. But right now we're working with the centrifugal, and we would just specify our change in pressure, 4 bar. Let's say 4 bar. That's what we want, and boom. It also has a pressure ratio attached to it, 4.948, and we head back to the worksheet, and it has manually imputed our final pressure for us to be 5.013. So if you do the change in pressure thing of final pressure minus initial pressure, you would see that we are having a positive 4 as our change in pressure, like we did earlier. So those are the 2 ways to actually do it. That's it for the compressor. And then for the 11th equipment, which is our expander. Did I say 11th? 13th equipment rather, our expander. So for that, you can see the expander is the opposite of the compressor. Even in terms of the design in 2D, it's just the compressor the other way around. That's what the expander is basically. So you would just double click on it. It's just like the compressor. Everything is the same. It's just the functionality. The compressor increases while the expander decreases the pressure, the volume. The compressor decreases the volume to increase the pressure, while the expander increases the volume to decrease the pressure. So we would now attach the compressed 3. That's our compressed gas, and we call it expanded expanded 3, and then it also requires an energy sphere, and we call it EXP, energy expander. And let's head to parameters and just include our change in pressure. It's supposed to be a decrease right now, so let's say a -4. We're having a -4, and our pressure ratio is 0.2021. We can see, okay, we're good to go. Means just successfully operated. Now we head back and we can see we are back to our pressure of 1.013 bar. With that, we have successfully operated our expander also. And that's it for today. With this, we could say we've successfully swallowed what we bit on. We went through the separator, the two-phase separator, horizontal and vertical. We went through the three-phase. We went through the tank, both the spherical and cylindrical tank. That's the liquid storage tank and the gas storage tank. We went through the compressor. We went through the expander. And with this, we are done with today's very, very long content. Hopefully you followed us down this far. Please make sure to subscribe, like, and follow, as that motivates us to create more content like this. Thank you very much.